Last year you learned a lot about conic sections in your pre-calculus class, and maybe you've forgotten a lot of conic sections. Let me talk about some of the things you'll need to remember for this year in order to graph conic sections. Like suppose you're asked to graph y equals negative square root of 3x squared minus 4. Well, you probably would reach for your graphing calculator, but unfortunately you're on a desert island and there are no graphing calculators around. So what would you do? Well, let's get rid of the radical. Square both sides of this equation. I know that will introduce extraneous roots or extra parts of the curve, but we'll get rid of them later. So this leaves you with y squared equals 3x squared minus 4, and then we'll do a couple of other algebraic manipulations. We'll move the terms around so that x squared and y squared are on one side. We'll divide by 4, and we'll also take that 3 and we'll put it into the denominator of the denominator. So it becomes x squared over 4/3 minus y squared over 4 equals 1. And then we'll rewrite it as x divided by square root of 4/3 squared minus y over 2 squared equals 1. And I know that this expression in the denominator is not simplified, but we won't worry about it right now. It's some number a little bit bigger than 1. And this is a very useful way to look at it because it corresponds to a simple parent graph x over a squared minus y over b squared equals 1. And when you replace x with x over a, that is just a horizontal dilation. Similarly, if you replace y with y over b, it's just a vertical dilation. So we're looking at a parent graph x squared minus y squared equals 1. Let's just look at the graph of x squared minus y squared equals 1, and then through dilations we'll understand how our graph is supposed to look. All right? What's the graph of x squared minus y squared equals 1? It's just a pair of diagonal lines. They make an X. Do you believe me? Probably you're thinking, that shouldn't be a pair of lines, it should be a hyperbola. Because after all, if x squared minus y squared equals 1, then x squared can't possibly be less than 1. So there's some region between x equals negative 1 and x equals positive 1 that should be excluded. But if you look at this, the part of your graph between negative 1 and, well, wait a minute, there's no scale on that graph. Could you please put a scale on the graph? Okay, well there's 1 million. Oh, well that's why it looks like an X. It's because hyperbolas really are X's. They're practically the same thing. In fact, they're the same thing except for right in the very center. So let's zoom into the very center to see why this is really a hyperbola and not an X. We'll mark off negative 1 and 1 in the X and Y axes, and then we'll recognize that X has to be excluded from that region. Let's also put the two lines that we saw in the previous graph, but I'll draw them as dotted lines. They are the asymptotes of the hyperbola. So we can draw a nice little square that shows a couple of things at once. The diagonals of the square are going to be the asymptotes, and the intersections of the square with the axis will give us the vertices. That is, when y equals 0, x is plus or minus 1. And now, to draw my hyperbola, all I have to do is trace along the asymptotes until I get near that square. And when I get near the square, I'll curve in and make sure and go through the vertex. And I get a very nice, accurate graph of a hyperbola. Now, I can graph hyperbolas that are dilated horizontally and vertically. Remember, we want to now stretch this vertically by a factor of 2. We want to stretch it horizontally by a factor of square root of 4 over 3. Remember where those numbers came from? The square root of 4 over 3 was that thing in the denominator in our equations. Let's go back to our original equations, and we'll take the same sort of graph and we'll dilate it vertically and horizontally. The square will become a rectangle, and we can draw the asymptotes through the diagonal of the rectangle. Notice, by the way, that this asymptote has the equation y equals negative square root of 3x. That is the same as the equation you would get if you ignored one of the terms in the original equation. If you ignore that minus 4, the equation becomes y equals negative square root of 3x. In other words, when that term 3x squared it becomes so big that the 4 is negligible next to it, the hyperbola will be extremely close to this asymptote. So it makes sense. It's a sanity check that this would be an asymptote of our graph. And I draw the hyperbola the same way I drew it. But you have to remember that we are graphing now the squared equation. The original equation is only part of the curve I just drew. Which part is it? Well, notice that y must be less than or equal to 0. So all we have to do is erase 1/2 of the curve. And please make sure to put filled circles on the endpoints of your curve. And there it is. We have a very realistic looking graph of y equals negative square root of 3x squared minus 4. This was done without a calculator and without even using graph paper, simply by knowing that the square root of 4/3 is a little more than 1. So please check this yourself. Take out your calculator, type in this function, let x go from about -3 to +3, use a zoom square so the x scale and y scale are the same, and you'll be astonished at how accurate this graph is. So that's pretty much all I have to say about graphing things of this form. There's a couple of more things to mention about conic sections. First of all, suppose I replace the 3x squared minus 4 with a 3x squared plus 4. How would that change things? It would make the hyperbola have a different axis. And once again, remember that you have to erase half of the hyperbola. In this case, again, the upper half has to be erased. What if you had, instead of 3x squared minus 4, you had 4 minus 3x squared? Well, that would be an ellipse. And once again, you have to get rid of the top half of the ellipse. So let's see. So far we've done 3x squared minus 4, 3x squared plus 4, 4 minus 3x squared. Do we need to do 4 plus 3x squared? No, that's the same as 3x squared plus 4. But wait, do we need to do -4 minus 3x squared? No, we don't need to do that one either. And you should figure out why for yourself. All right, we've talked about hyperbolas and we've talked about ellipses, but you probably remember there are other conic sections also. There are circles, there are parabolas, there are lines. Why are we ignoring them? Well, the parabola is a special case that occurs right between the hyperbola and the ellipse. And the circle is a special case of an ellipse. Lines are a special case of a hyperbola, or they're a degenerate hyperbola. You should be knowing how to graph those as well. Also, remember that the center of the conic is not always the origin. So sometimes instead of x squared and y squared in your numerator, you could have x minus something squared and y minus something squared. And the graph is just going to be a translation. So if you have those pesky linear terms in your expression, just complete the square to get rid of them and do the translations. Make sure you remember how to do that. There's a lot of more things you could remember about conics. You could remember why those curves are sections of cones. You could remember the significance of the focus and how they could be constructed geometrically. But those things, although they're fun to know, we're not going to use them a lot this year, so you may look into them on your own, but I won't discuss them now.